Hi, and welcome again to ABE 121. This is AB Structures Engineering, and we're still on the topic of the design of members or parts of AB buildings and structures. Particularly, we're on the topic of the column, okay, which is going to support our beam, which was the topic before this lecture. Now, uh, let me just move forward my slide. All right. So we have here images of columns, an, an, probably an ancient type of column, and we have columns, wooden columns. Uh, this one is a concrete type, while this is wooden. Now imagine a certain column as this uh, in this diagram represented by this uh, block, okay? And when you have a certain force over here, let me just use a different color. So you have a force over here, right? And you have another force, but there's going to be a reaction force at the other end because of this force. Let's say it's P. For certain types of columns, particularly the short ones, it's purely a compressive stress that the column under experiences. Thus, there's no what we call um, a deflection to this to a certain lateral direction. But if a column is long, okay, it may experience a certain uh, deflection that is going to be something like this in form or in uh, shape or uh, figure, okay? And this is what is termed as buckling, okay? Buckling. The lateral deflection of a column. Again, this only happens in long columns. Now let's proceed with so that's what it really is, okay? There's what is called buckling. So a column is actually a compression member that fails by crushing or buckling. And when buckling happens, it's for significantly long members or columns. Now, there is a certain factor that is considered in the degree of the longness. Okay, there's slenderness ratio. Okay, and it's represented by the symbol lambda, and it's equal to L over R, with L the effective length of the column. And to get the effective length, there's a certain factor K that is multiplied to the uh, actual length of the column. And the factor, this K, is dependent on the condition, okay, at the ends of the column. And we'll see how this differs in a while, okay? Now, KL over R is an, a value determined using the moment of inertia, and this is the radius of gyration, and it's equal to the square root of I over A. And the I, okay, it would depend on the cross section of this of the column, okay. And figure 1 shows the different cross-sectional shapes that are being used in the design and construction of columns. Now, A is the cross-sectional area. I is representative, it is the moment inertia of the cross-section, as shown on figure I1. Okay, and to get R, okay, these two should be uh, clearly identified. Okay, these two, okay, I and A should be clearly identified, and it's very simple to determine that as a uh, prerequisite of this course. Okay, the student has to be able to solve that already in the course. Okay, strength of materials or mechanics of materials. Now, the column failure is dependent on the column material. That would state the E, or the modulus of elasticity of the material, representative of the allowable compressive stress. And we have the cross-sectional shape, obviously, because it would dictate the radius of gyration, and the column ends, because it would dictate the direction and position of the uh, column, if it's fixed in position and direction or not. All right, now let's go to this uh, column ends. Okay, but before we do, let's have an example with short columns that are uh, failing, or that fail due to compressive stress solely. Okay, or this is in terms of crushing, and we have the formula A, which is equal to F over sigma. Okay, with sigma as the allowable compressive stress, that is, uh, it's dependent on the material of the column. So we have uh, this material directing the degree of allowable force a in the column structure. And let's have this an example. Okay, a column, a concrete one, that is zero point 0.4 meters high, is made of a concrete mix of 1:2:4 with maximum allowable compressive stress of 5.3 megapascals. What is the cross-sectional dimensions of the column that is square in shape and required to carry an axial load of 300 kilonewtons? All right, so this, I think, is very direct. We have a certain square, a square shaped column. Okay, we're not going to draw the whole column. Okay, just a representative of it. So there's a certain force over here, 300 kilonewtons, and we have the allowable as 5.3 megapascals, and we have a concrete mix of one. I think that's very just a given that is not important to the solution. Okay, so how to solve this one is okay, we have the formula A equals um, F over sigma, and we have 300 times 10 to the 3 newtons over 5.3. This is times 10 to the 6th pascals. And so we have, and using my calculator, we have this as 300 divided by 1,000, 300 times 10 to the 3 divided by 5.3. This is, okay, let's try to correct this one. I mean, it's actually correct, but we just want to simplify our solution. This is 300. This is Newton per mm squared, so that what we'll get eventually is in millimeters. And we got value 56, sorry, this is 56,604 mm squared, right? Since this is a square, okay, what we'll do is, since we have the area as just s squared, right? So we have s as the square root of 56,604. Sorry, it's a 0 mm squared. Let's just correct this one. Apologies for my what happened. So I did not I think the solution got erased. I'm not sure what happened, but let's just rewrite this one. Okay, so this is 56,604 Newton per mm squared, and we get s as square root of 56,604 mm squared. We get the value of 238 millimeters, right? So this is the final answer. Very simple. Very direct to the point. All right, let's proceed with what happens to the column with different positions or conditions of positions and directions at the ends. If there's a fixed member, so there's no change in direction or position at the ends. The value for k is what is the minimum is 0.5, but the actually used is 0.65, right? So try to make use of this value instead, okay, of the you have to make use of this one instead of this one, right? For a column that's fixed on one end and the other is just pinned, so there's a possibility of the movement in terms of the direction, so it can move, okay. A certain kp of 0.8 is used instead of 0.7, but this is the average, okay, or the minimum that can happen or can be used. But instead of add some safety factor, make use of this one. For pinned in both ends, you just make use of k equals 1.0, and if it's a free end on the other end with a fixed end, well, just one end is fixed, you have a k that's equal to 2.0. Right, so this is the effective length factor k. And let's go to the materials, okay? So we can have concrete columns as possible. This is concrete, okay? Concrete. We have concrete walls. So concrete walls are treated as columns, very long columns. And they can either be just plain or centrally reinforced, meaning we have a reinforcing steel bars in them. That's centrally, okay, placed, okay. So centrally placed. So another thing is we have steel columns, and lastly, timber and wood columns. And for all of this, the loading could be axial or eccentric, and we'll introduce this eccentricity ratio later on, right? So let's proceed with table 1, which is the allowable compressive stress in concrete columns, and it's based on the Slenderness ratio. Again, this is taken from FAO 2011 reference, as will be seen later. And we have the concrete mix in this column. Over here, different Slenderness ratios. Now, take note of the Slenderness ratio here. It's not L over R. Instead, there's an arbitrary ratio used that's called L over B. The B is um, the dimension, okay, of the column in the cross section, and it's best to solve for both dimensions if the dimensions are not the same, meaning could be a rectangular or as long as it's not square, because if it's square, then automatically it's just one dimension. So for this is for concrete columns, right? Okay, so we have different concrete mixes having different uh, values for different, okay, different slenderness ratios. That's why we have this matrix of a column of a table that's used. So we have the prescribed C10, C15, C20, and so the nominal concrete mixes for uh, cement, sand, and gravel. Okay, and the way to use this is to simply interpolate the values if ever the slenderness ratio is say in between 10.11, so it's from 10.00001 to 10.999999. Okay, so it's best to interpolate in these values. Also for other uh, slenderness ratios, okay, in between those values. Right, example. Determine the allowable axial load of a concrete column with effective length 4.5 meters and cross-section of 300 millimeters by 500 millimeters of a nominal concrete mix 1:2:4. Okay, so uh, the best thing to do is to directly compute for the slenderness ratio, which is L. Sorry, I think I'm using a black ink pen. So it's L, that's equal to L over, sorry, this is gamma, lambda, L over B. Okay, so we have 4.5 meters over 0.3. We use the one length, okay. We're assuming it's a smaller B because it could happen in that along the direction, okay. It's the slenderness ratio is longer along that side. So we get a value here, and automatically, since we're not looking at, we can easily get for the value of the 1:4 mix with the 15 slenderness ratio, and it's simply this one. It's 3.3. All right, so it's 3.3, and you can easily make use of that here. So we have, hence we have sigma equals 3.3 megapascals, and then we can easily solve for the force, okay, which is sigma A, and we have a rectangular shape column, the cross section of which, okay, and we could easily solve that by simply multiplying 3.3 Newton over mm squared times 300 millimeters times 500 millimeters, and we get how much this is 3.3 times 300 times 500, it's 495,000, okay, 495 kilonewtons. Okay, next we have here for spleen and centrally reinforced concrete walls. And again, we have these walls treated as very much like columns that are very long. And the only difference that's considered here for a concrete column is that the length of walls is 5 times the thickness. So very long indeed. Okay, and the minimum required wall thickness is 100 millimeters. And we introduce here a uh, factor or a parameter, okay, the eccentricity ratio. And this simply just means, okay, the eccentricity ratio is a value used to determine if, okay, a reinforcement is needed for the wall, okay, a reinforcing bar. So this eccentricity ratio is E over P, with E the distance of the load, okay, the loading to the center of the wall, and this is uh, has a certain limit. So we have, if the eccentricity ratio exceeds 0.2, there's a need for reinforcement of 0.2%. Okay, but the reinforcement, okay, is not used in the computation of the load carrying capacity of the wall. Okay, unlike in beams. Now, again, a table here is used for the determination of the compressive stress for different concrete mixes. This is not a complete table. The reader or the viewer is advised to look at the FAO uh, uh, reference material for this complete table. It's Creative Commons text, so anyone has access to that. Now, uh, the eccentricity ratio differs for plainly concrete walls and for centrally reinforced walls. And okay, again, the values could be interpolated, okay, in between this um, these figures, okay, or this values over here. Okay, this one in here. Okay, another thing, interpolation could be done along this area, along this line, okay, along this row. Okay, so in between 21, there's 20.001 to 24.0 for 0.99999. So anyway, something like that. Now, uh, let's start to make use of this one with an example. Determine the maximum allowable load per meter of a 120 millimeter thick concrete wall with effective height of 2.8 meters if the load is eccentric by 20 millimeters, and use a concrete grade of C15. All right, let's try to imagine the wall as something like this, right? It's very long, and at the cross section, we can see that the thickness is what? It's actually 120 millimeters, and you have his as a center, okay, and the load is eccentric by 20 millimeters. This is 20 millimeters, right? And the height is 2.8. So we have already an effective height of 2.8 meters. Now to solve, okay, we get the eccentricity ratio of 20. Eccentricity ratio, okay. Eccentricity ratio is equal to E over P, which is 20 millimeters over 120. And it's 0.167. It's unitless. And when you get this value, okay, since we have the um, slenderness ratio as, okay, slenderness ratio is, effective length is 2.8 meters over 120, 0.120, or 0.12, and we get 23.3, right? C15. So we have here in the table C15, right? So it's 23.3. It's between this value, okay? It's 23.3, and we have the, so it's 23.3. Try to double interpolate this one, 23.3, and we have the value of 0.167. It's in between this value, it's 0.167. We try to get this value, right? 1.3, 1.9, 0.7, 1.1. Okay, so it's try to recreate the table here. So we have the value 0.10, and we have 0.167 here. We have 0.20 here. Trying to find, this is 25, this is 20. We're trying to find 23.3 of the lambda, or the slenderness ratio, and we have ER over here. The values are 1.3, 1.9. We have 0.7, 1.1. So we're trying to find this value. And we do so by either solving this one and this one first, or this one, and then eventually that one. We will get the value of 1 point, let me see, is 1.06 MPa. Okay, so the value of gamma, sigma is 1.06 megapascals, or Newton per mm cube, squared. To solve for the allowable load per meter is we simply now multiply this by, okay, allowable force is 1.0 times 0.12, okay, times 1.06 Newton per mm cube squared. And we simply get here, oh, sorry, I think I'm solving this wrongly. It's this is 1 meter, 1 meter. So you use 1,000 millimeters here and just get 120 millimeters. Get, so that we have similar units. Okay, 1,000 millimeters times 120 millimeters, and we get what? 1,000 times 120 times 1.06. It's 127,000. Okay, it's 127.2 kilonewtons per meter of wall. Okay, so this is the final answer. All right, let's proceed to steel columns. Still, we are going to make use of the effective length K to determine the slenderness ratio. And we use the cross-sectional moment of inertia to determine the radius of gyration R along the two cross-sectional axes. But we use now a certain table 3, okay, to determine the compressive stress for steel columns, okay. And sorry, this is steel, okay. This is not concrete. This is supposed to be steel. You have this as steel. Columns. Apologies for the typo. So we have here the slenderness ratio, okay, along this line, in this row, and we can easily determine the K. That is a reduction factor multiplied to the F over A, or force over area. Again, this is interpolation determined. Okay, the values are interpolated here. If you have middle values, again, example. Okay, calculate the safe load on a 3-meter high, hollow, 6mm thick square steel column with external dimensions 120 by 120 millimeters. If the allowable compressive stress in was 150 MPa. Both ends of the column are held in position, but only one end is restrained in direction. So we have a column that's square in dimension. Okay, we're not going to see the fixed, but this just say that this is fixed position and direction, and let's say that this one is fixed in position. This is 3 meters, and we have the thickness as 6 millimeters, and the dimensions, right, it's 120 millimeters. Okay, it's also 120. To solve for this one, okay, so we have here Rx and Ry, okay, the radius of gyration as the same along each dimension, since we have similar dimensions. Okay, it's a square, and we have is as square root of I over A, and it's simply square root of BD cube minus BD cube all over B. This is over 12, right? 12 times BD minus BD. So we have this as 120 to the fourth minus 108 to the fourth over 12 over 120. This is squared, okay? This is squared. (120 squared minus 108 squared), and we get the value of, okay, we're going to look at or solve this. We get the value 46.6, right? Now we have a fixed position over here and direction, so we use the K equals 0.85. So the effective length is going to be KL, or the slenderness ratio is going to be, let's go directly to the slenderness ratio. So the slenderness ratio is KL over A, and it's 0.85 times the length, which is 3,000. So it's 2,000. Oh, this is over. Sorry, this is not A. This is R. So apologies for that. This is R, and we get this as 46.6, and this is what? This is the value is 54.3. And since we have the value that's not exact to the values in the table, okay, we interpolate between 50 and 60, and we get, okay, it simply is, it's a very simple solution. We just interpolate. We have the values 0.86 and 0.81. So the value of sigma is, okay, it's 0.86 plus, okay, the value of this one, what's that? This is the value is going to be, okay, 54.3 minus 50. This is 60 minus 50. This is going to be 0.81 minus 0.86. Right? So you're going to get a sigma here that is, try to solve if it is correct. That's how to interpolate, okay? 60 minus 50 times 54.3, or 4.3 times 10 divided by 0.81 minus 0.86. Okay, so this is going to arrive at a value that is 0.8385 megapascals, or Newton per squared. And we can simply compute for the F, or the PW, okay, or just assume it's F. So it's sigma times the area, and we get a certain factor, right? So we have introduced the factor here, okay. Oh, sorry, apologies, this is not sigma. The sigma is already given. We were trying to solve for the K. This is not sigma, this is K of the slenderness ratio, the reduction factor. I forgot, okay? This is K. So we already have the 150 megapascals times the area, that is, so the K has no value. This is no value. So we have here as, okay, to simplify our solution, we already used the Newton per mm squared times the area, which is, make use of more space, since the answer is wrong. We use, I forgot that this is a hollow one. So we have the force as, okay, K sigma A, and we have this as 0.8385 times 150 Newton per mm squared. Okay, and then we multiply this by 120 squared minus 108 squared. This is going to be in millimeters, and same, so that we get the value. It's 344, I think. 120 squared minus 108 squared times 150 times 0.8385, 344. Okay, it's 344 kilonewtons. Okay. That's the final answer. Now we move to wood, and the same analysis is being used for wood as with steel columns. The only difference is the reduction factor, since we have a different table that's being used, and we can make use of the arbitrary slenderness ratio L over B, or the exact, okay, slenderness ratio L over R. Again, we use the K to determine the slenderness ratio, and we use the I to determine the R along the cross-sectional axis, and use the formula shown for sigma. Again, we are interested in determining the force, allowable force that a column can bear, or get the dimensions of the column if we have a known specific load that the column will be experiencing, and we can determine that using our given of compressive stress, okay, and dimensions or specifications. There's a simplification to the computation of timber or wood columns, and it's this this consideration. Okay, we have the classification based on certain values. Okay, if the slenderness ratio is less than or equal to 11, it's a short column. But if it's based on this arbitrary number or factor K, which is 0.671 times the square root of the quantity E over the allowable compressive stress. E is the modulus of the elasticity of the wood. This K is the limit, okay, to determine if it's an intermediate column and long column. Again, the computation will proceed as follows, okay? You just have this as the design criteria, okay? If it's short, if it's intermediate, or if it's long, and then proceed with the same computations to determine again the axial compressive load allowable. All right, so that's all. Here's the reference. It's really available over the internet, and I'll see you again in the next discussion, and we'll cover flooring systems. Thank you for listening, and I'll see you next time.